Welcome back, everyone. So today we are again going to stray further away from linear algebra and work on permutations. And permutations are essentially just the number of possibilities whenever you have a given number of, for example, cups and a given number of items that you can put inside of them. So the total number of possibilities for each cup, for example. That's just an example case. So let's just write the title. Get in a better position. Permutations. So let's start off by giving you a visual representation of this. So let's say we have 4 cups. Right? Let's say we have 4 balls. Let's number them ball 1, ball 2, ball 3, ball 4. And basically, essentially, it's figuring out the number of possibilities that can go into these cups is quite trivial. Here in this first cup, there are 4 possibilities, right? We have four available balls. So 4. Here, one of these 4 slots is taken, so now we only have 3 in this one. Whoops. 3 in this one, and so on and so on. Right, again, revisiting this. You have 4 total here, but now since one of these 4 possibilities has already gone here, you get n-1, or the number of these balls, in this case. So you get 3, and then you continue that pattern until you get to 1. Or that's not actually valid until you satisfy all the cups in this case. So to get all the possibilities, since you have the possibilities for each one, you actually just multiply the values inside the cups, and you get 4 factorial, actually, which is quite nice. You get 4 times 3 times 2 times 1. And that's just equal to 12. That's just equal to 24 possibilities. Right? So now we can look at another example. In this case, we can have 3 cups. This will be a bit different. And we have the same 4 balls. Right? So now let's try using the same procedure. So we have 4 possibilities. Whoops. My bad. So we have 4 possibilities here. So as a result, we can put 4 of these balls in this cup. Again, same procedure, 3 and 2 in this cup. Now you can see it's similar to 4 factorial, except not exactly, since we're missing the 1. Even though the value would be same without the 1, it's still a different scenario. So in this case, we can actually express this as 4 times 3 times 2 times 1, which is just 4 factorial on the top, over 1. Now, it's not as obvious here, so I'll give you guys another example in a second. But what I want to get at here is that basically you can think of this as, and by the way, this is the notation that I like to use. So the number of permutations for n items and k containers, for example, in this case can be equal to this number, or this number factorial, so n factorial over n minus k factorial. And the reason I don't use this formula very often is because it's kind of just, it's not very obvious at the start, but we can just look at it real quick. So n, meaning the number of balls here, and K, you can remember it as cups, so K for cups, even though it's C for cups, but that's the way I like to remember it. And it's not always going to be cups again, but that's just the way I like to remember it. So we can use this formula. I wouldn't recommend using it. I would just recommend using the more simple, intuitive path rather than this path. It could be more useful for a bit larger numbers, but I just prefer using this path. So I'm just going to show you that these are equivalent. This way and this way are equivalent. So n factorial, which is just this number, over here, I'll just take a shortcut and we'll say that we started here. And n minus k, so that's 1 factorial, which is also 1. So 1 factorial equals 1. You cancel the 1, and there you go. That's your answer there. We can use another example. Just going to erase this. Okay, let's use another example. Let's say we have 6 happy faces, right? 6 happy faces. Thoroughly deformed happy faces, furthermore. Okay, and then let's say we have 4 cups. I guess 4 cups. All right, so now we're going to use the same procedure, the intuitive procedure, then the formula. So essentially, you can use this to derive the formula. So we have 6 possible happy faces that we can put in this cup. So we have 6 times 5 times 4 times 3, etc., etc. So, yeah. Here it's, again, you see the pattern. It doesn't go all the way down to 6 factorial. That would be 6 times 5 times 4 times 3 times 2 times 1. It just goes down to this portion here. So again, we can express this as 6 factorial over n minus the number of containers. So we're going to write it out, actually, just to give you intuition, right? And that's what we're all about. So happy faces minus cups factorial. Okay, so we can write that as 6 times 5 times 4 times 3 times 2 times 1 over happy faces minus cups. That's just 2 factorial, actually. So that's 2 times 1. You can cancel the terms, and there you go. We get the same answer, just like so. 6 times 5 times 4 times 3. That's equivalent to 360, I think. I believe so. 360. So that's equal to number of possibilities equals 360. Okay. And again, let me just retrieve back to the formula. N again just describes the number of objects, in this case item, in this case happy faces, and then the number of containers in this case, or the number of possible choices that these, we're personifying these happy faces, but the number of choices that these given objects can take. And the number of possibilities is 360, right? Because 30 times 4 is just 120 times 3 is just 360. Anyway, hopefully you enjoyed that video. I might do another video, or I might do a video on combinatorics, but I might do another video on this, just a more in-depth video. So hopefully you enjoyed, and have a nice day.